Let's wait for 2 3 minutes and then I will okay. Let me start. So this is week 3, problem solution. The course. Okay. So the main plan today is that we will discuss about the assignment 1 and assignment 2 questions. And once we have understand this those questions, then we will go towards the week 3 content so that we can solve the week 3 assignment questions, something related to that. So those things we will try to see. Okay. So let me start with week 1 assignment. So week 1 assignment consists of too many numerical questions, which I have seen so far. And week two only is only having one, and mostly based on whatever is covered on uh, the previous problem solving sessions. If you have gone through, you will be able to understand that or understand and do those questions. Okay, so let me directly go to the assignment one, which is assignment one. Just taking a PDF of that. Okay, so if you look at the first question, it is asking which of the following is not a body force. So in the first problem solving session, we have discussed about that the force, particularly the forces which are present in the atmosphere, can be categorized based on whether it is acting on the body or at the surface. So that categorization is made. Second is that we have categorized the forces on the basis of the frames of reference, whether it is inertial frame of reference or non-inertial frame of reference. So in that way also we have categorized the dynamic forces. But here we don't need that second, the latter categorization, that is forces based on your frames of reference, but it is based on where the force is being applied. So there are four options. One is the gravitational force, second is frictional, electric force, and magnetic force. See, electric and magnetic force all are body forces, definitely, because uh, if you see the basic physics, whenever you talk about the electromagnetism or your electric forces or magnetic forces like the Lorentz forces and all those forces, those generally acts on the body. Okay, gravitational force, particularly this particular force, is for the atmosphere, particularly the weather phenomena and all those things. This gravitational force uh, has a tremendous effect. And we have seen where the gravitational forces act. That is, if you consider Earth, it will act towards the center of the Earth. We have seen it for a long time, right? And there is also a question, the second question only. We will derive certain things which I have already derived once. So you will see that gravitational force acts towards the center of the Earth, and which is nothing but a body force. So towards the body of the Earth, the force is being applied. So all three are body force except for the frictional force or viscous force. If instead of frictional force had it been given the viscous force, so that is also a surface force, because you know that friction is at the surface. When you have a block on the floor or on anything which is having some coefficient of friction, which is mu something, you know that at the surface there will be an opposite force in the opposite direction to which the actual force is being applied. So without going into too much of details, it is very clearly known that frictional force is not a body force, it's a surface force. Other things are body forces. Okay, so I am not going into much more detail on that. So it is a known kind of a thing. It's a kind of a known force, which is a surface force. Okay, the second one is that imagine a planet that has same mass and radius as that of the Earth, but that makes 20 rotations during the time the Earth makes one rotation. So when you have a 1 day is our rotation period, right? So when the Earth rotates by 1 day, the planet rotates 20 rotations. Okay, so what would be the acceleration due to the gravity? Very important is these last three words at the planet's pole. So at the planet's pole, so it is already saying that don't calculate the gravity only, but tell me what is the gravity or acceleration due to gravity at the planet's pole. So for that, we'll do some little bit of derivation, particularly for this word, that planet's pole. So let's come here. So first answer was the frictional force is a surface force. So I just quickly write it for the first question. Okay, it is a surface. It's not a body force. Simply because this is a block having mass m. I have given a force, suppose F, and based on the coefficient of friction, mu is equal to something 0.25 roughly. So there will be a force which will be applied here. This is the frictional force. So frictional force is a surface force. At the surface of the body, it is acting. Okay. The second one is saying that you consider an arc like an Earth-like case, Earth-like body, or a planet, which is, let's say, I'm making a 2D Earth for the time being, let us say, which has the mass. So let us, I'm denoting this dash as the planet, the imaginary planet. So m dash is equal to me, the mass of the Earth. Okay, and the planetary rotation is say omega dash. And what is this omega dash? Is nothing but 20 times omega. Correct? Because omega is the planetary rotation. So planetary rotation is calculated simply by this 2 pi divided by the time period. Because 2 pi radians means one rotation it does in 24 hours. So 24 into 3600 seconds, right? So if you put this 2 pi divided by for Earth actually, so 24 into 3600 seconds, it will come out to be 7.25 into 10 to the power minus 5 radians per second because this 2 pi is in radian. Okay, so this is your angular velocity of the Earth. But it is saying that it rotates 20 times the Earth rotates in the same time in one day, 24 hours into 3600 seconds. The planet rotates 20 times. So it's 20 times omega simply. Okay, so this is the second information which is given in the question. Okay, now it has been asked that what will be the gravity, acceleration due to gravity g dash of that imaginary planet at pole. So let us first derive the expression of the Earth's gravity and different latitudes. Okay, so we need to, so let us for this let us derive gravity g for different latitudes. How g varies with latitudes. Why latitudes? Because in the question it is asked as pole. So you know that this is equator. This is, as you move like this, these are the latitudes. Okay. And at pole, the latitude is 90 degrees. Right. So we know this. This is the basic thing which all know, all of us know. Okay. So this is what we will be trying to do. Okay, and okay, so what will be your G dash in general? G dash will be nothing but gravitational constant G m dash divided by R dash. This R dash is the your radius. Okay, in general, but we need to find out G dash at poles. So we need to see how G varies with latitude. I have already shown, but let me derive it once more so that it is clear with the question. So let us consider the case of Earth only initially, then we will see. Okay, so this is your equator, 0 degree, and let's say this is some angle phi. This phi is the latitude. Phi is the latitude. Okay, so phi is the latitude. Okay, now suppose here there is a unit mass which is present at the surface of the Earth for the time being. Okay, and this is your R. This R is the radius of the Earth. I'm not saying the radius of any planet. Right now, it is the radius of the Earth. We can change it later on. Okay. Now, where is going to be the gravity force? Actual gravitational force. It will be towards the center of the. This is known to us. This will be G. Okay. At the same time, at the same time, if this is R and this is the unit mass, where will be the centrifugal force? Because is having a rotation, right? So there will be a centrifugal force because of the rotating frame of reference. So the centrifugal force will be a center force which is acting outside the body. So it will start from here and it will try to pull it or push it outside the Earth's surface. Okay, so this is your centrifugal force, which is nothing but your r cos phi omega square. Why r cos phi? Because this is r. This radius is r. So if this is phi, this is also phi. So this will be what? R cos phi. All right. So remember, this is your r cos phi omega square. And why I have not put mass here? Because mass is unit. So unit mass. Okay. Considering unit mass. Done. This is clear. Now, because of the center of this gravity, actual gravity, and there is a centrifugal force which is also acting, there will be a resultant gravity. Okay, there will be resultant gravity, which is centrifugal force is very less, so the resultant gravity will be more towards the gravity force. So this is suppose g dash. Okay, so or let us say okay fine, g effective you can say g effective. Okay, so G effective square. This is the parallelogram law of vector addition. So G square will be equal to G effective square equal to G square plus FC square, because the two forces you have to square, to cos square phi and omega to the power 4 plus 2 times the first force, the second force, times cos of the angle between them. So what is the angle between them? See, this is your pi, already known. Then what is this? According to the linear pair, this angle should be 180 minus pi. Just think about it, it will be easy for you. Okay, this is what your parallelogram law of vector addition gives you. So you have g square plus r square cos square phi omega to the power 4. Now cos 180 minus phi, what it will be? Since there is 180, cos 180 minus phi will be cos phi, but 180 minus phi is in the second quadrant. Second quadrant, cos is negative. If you simplify trigonometry, all sides tan cos. So in the second quadrant, sine is positive, cos is negative. So it is minus 2g r cos phi omega square cos phi. Perfect. This is what you get. Now, what is the value of omega for the earth? Because we are all deriving for the earth. Is about 10 to the power minus 5. Right? Now, if you do omega to the power 4, it's very, very small, right? So, can we neglect this term? Yes, as compared to these two others. So, g effective square, therefore, is g square minus 2g r cos phi omega square. And this cos phi also you multiply, so it will be cos square phi. All right. So finally, if you do all these things, or let us do it, okay. So it will be root over omega square. And let's do one thing. Take the g out of this. So what you will get? 1 minus. So see, from the root we are taking g square out. So that's why I have written g here. So it will be 2 r by g cos square phi omega square. Correct? This is what you will get. So g into 1 minus 2r omega square g and cos square phi to the power half. Perfect. Now use binomial expansion, just a simple step, and neglecting higher order terms because omega will be too small. So it will be 1 plus, okay, wait, yeah. So no, it will be 1 minus, it will remain 1 minus because it is to the power half. So it will be 1 minus 2r omega square cos square phi divided by g and 2, right? 2 cancel. Finally, you get g into 1 minus r omega square cos square phi divided by g. That's all. Now you just multiply it to g minus r omega square cos square phi. That's all. So this is your g effect. The effective gravity due to the centrifugal force is this in the rotating plane. Now see there is a latitudinal variation. Now if you put phi is equal to 90 degree, which is for poles, what you get? G effective will be equal to simply G because cos 90 is 0. Right? So G effective will be equal to G. So this is very important. Okay. So now if let us consider this, right? Your G dash. Look at G dash, right? So now in the imaginary planet, for the imaginary planet, for the imaginary planet, if you apply the same expression, so G effective dash will be equal to G dash minus R omega dash square, cos square phi, right? This is what the expression will be. Now, omega dash will be equal to 20 omega, but G dash, what is G dash? We have seen G into M by R square. R is not changing, right? Because it is still the same as the Earth. So this G dash is actually equal to G of the Earth, which is about 9.81 meter per second square. Yeah, something like that. Okay, but at pole, this term is zero. So omega dash, if it is 20 omega, it does not matter, right? So at poles, or at the polar region, G effective dash for the imaginary planet is nothing but G dash, which is nothing but G of the Earth, right? So this should be the answer. That is 9.81 or 9.78 something. So let's come to the question again. So 9.8 meter per second square. This is the gravity of the Earth. So the planet's gravity is also the same. That's all. Okay. So yes. Okay. Fine. Let's come here. So your question is that why are we considering unit mass? Great. This is a good question. Just consider mass. So if you just consider mass here, multiply mass everywhere, it will be the same mass, right? If this have some mass m, everywhere it will be the same mass. So ultimately it will be considered. So whether you take unit mass or take some mass, if you take some mass, it will be always be cancelled. So whether you take unit mass or any mass, it will be fine. Okay, understood. Huh. Okay. So finally, the expression will be 9.8 meter per second square. So that is the thing. So there is no role of these 20 rotations. That's all. Fine. Third question is that assume that the Earth goes around the Sun in a circular orbit with a constant speed of 30 kilometers per second. So these are some questions, answers which have been provided. Okay, so the average velocity of the Earth from 1st January, some year to 30th June, some year is zero. Average velocity is zero. Then average acceleration is something 60 kilometer per second square. But if you look at all these four options, the most definite thing is that the D options, that is the instantaneous acceleration of the Earth points towards the sun. Look at this. So if you go here, so you have the sun here, and there is a circular orbit which is being given, right? So Earth is somewhere here, and it is of course rotating as well as revolving. This question talks about the revolution of the Earth, okay, with some velocity and what, okay. So you can check each and every options, but let us be very clear that when you have this kind of a rotation, there is always a centripetal or centrifugal force. So centripetal force is a central force, always a center directing force. So whenever when the Earth goes around this orbit, there will be always a center directing force, which is called the centripetal force. Remember, here the frame of reference is not mentioned. So when your frame of reference is not mentioned, in this case particularly, you always have to consider the centripetal force because it's a rotational motion. So centripetal force. Okay. Why not centrifugal force? Because see, whether it is a rotating frame or you are observing from a non-rotating frame. So whether you are observing from a rotating frame or non-rotating frame, one thing is common, this centripetal force, because this centripetal force is a real force. Remember, this centripetal force is a real force. It's not related to the atmospheric physics, but it is a very general physical question. Okay, so it's a real force, and it is a center directing force. So force and acceleration are same. So you can understand this. Per unit mass is the acceleration. So this real force will always be acting instantaneously towards the center, that is towards the task. But if you consider only the rotating frame, which has not been mentioned here, then you will say that no, there is also a centrifugal force, which is of the same magnitude of the centripetal force. That's all. That is the difference. So here, if you look at all the options, you will see that the most definite option is this, that the instantaneous acceleration is always towards the center, that is towards the sun. That's all. Okay. No need to. go to any other options when you have seen that this is the most genuine option. Okay, so this is another. Fourth question is very interesting, and it is very, I would say, uh, you need to think about that how you will solve this question. So let us try that. It is a very good question. So two balls of equal mass are placed near 43° north. Let's forget about 43° north for the time being, such that the distance between them is 200 meters. Each ball has radius of 4 centimeters. If the balls are set in motion directly to each other at equal speeds, see, each and every word is very important. So, at what speed must they travel so that they just miss each other? Okay. So, why they are asking about at what speed they travel such that they miss each other? Question is that why this question is there at all? Okay. So, let's understand this. Okay. The fourth question. Let us understand this. So, they are saying that let us make a imaginary distance. This is one ball, this is another ball, which is separated by center to center, let's say 200 meters. Correct? And this balls have radius, how much? 4 centimeter, right? 4 centimeter. This is what is given, I guess. Yes, 4 centimeter. Okay. So 4 centimeter is the radius. Okay. So you just write one that it is 4 centimeter. Okay. Question is that now what we have done is that we have given a velocity to this, we have given a velocity to this, and they are equal velocity. Some v, let us say. Okay. Equal velocities are given, and they're asking at what point or at what distance these two balls will separate each other like this. Okay. Uh, just a minute. Just give me a moment. Yeah. So they're saying that finally why these two balls will separate each other. Means they will not collide. They are saying that they will not collide. That what velocity these two balls will move towards each other such that they don't collide and they just miss each other. So how can it be possible that if you are throwing one ball and I am throwing one ball and we are opposite to each other and those two balls don't collide? This can happen because it is we are talking this thing is happening, this experiment they are doing at 43 degrees north. At 43 degrees north, the rotation, planetary rotation, becomes important. Why it becomes important? Because Earth is a rotating frame of reference. And whatever experiment we are doing, that is in a rotating frame. That's why they have talked about 43 degrees north. Okay. So rotations becomes important. That means what? Important means you have to include the Coriolis force. Right? Coriolis force is the force due to the rotation of the Earth, one of the forces, and I would say a force which has a relatively good magnitude compared to the centrifugal force. So this Coriolis force needs to be considered. That's all. Okay, that's why 43-degree north is being given, and the two balls will not collide because this ball, when they travel, they will have some rotation based on the velocity direction. Okay, so this is important. So we will see this. This question is very important, I will say. Okay, so let us consider. So consider these balls are thrown. So these balls are thrown at each other, whatever it is thrown in x direction. See, we have to use some kind of a sign convention. Otherwise, it will be very difficult. Okay. So let us consider that it is in the x direction. So let us say that x direction velocity is u instead of v. Okay. So this is what we have said, and the balls will separate in one y direction, right? Because of the Coriolis force, balls will separate in y direction. Okay, because the Coriolis force is always will always act perpendicular to the direction of motion. That is what is given by this. So when we have derived Coriolis force, you should have remembered this Fq cross B. So this cross product shows that they are 90 degrees at angle. Okay, so that is important. Fine. Let us understand. So we will apply the uh, y direction momentum equation. Y direction momentum equation. But in the momentum equation, in case of Earth, we have written so many terms, right? The pressure gradient force, frictional force, all those forces we will consider zero. Only force which is acting is the Coriolis force. So, based on the question, whatever information is given, assume certain things on your own. But whatever information is given, you have to use that information. Other things as zero. Okay. So, y direction momentum equation with frictional force and pressure gradient force, PG force, is considered to be assumed to be zero because it's nothing is given. Okay, no information is given, so we can't use that. So, what is the y direction momentum equation? dv dt, where v is the y velocity. So, y direction velocity. Okay, this is the y direction velocity. So, dv dt is just minus f times u. That's all. This is the Coriolis force or horizontal Coriolis force. We have derived that in the, I think, last session we have derived horizontal Coriolis force. Horizontal Coriolis force y component. That's why dvdt is this. Okay, just check the previous problem solving session. We have derived it. Okay, so if this is our momentum equation, we will proceed. So dv is equal to minus fu. A similar kind of question we have done in the last problem solving session. So you will understand. So you just take the integral of this. So v will be equal to minus fu t. Okay. Assuming at t is equal to 0, v is 0. After that, we have given some motion, and that's the way we are doing. Okay. So this now v can be written as dy dt and minus fu t. And so what we do is that same way dy will be equal to minus fu t dt. Take the integral. Okay, I'm not putting the limits because it's a very approximate way of calculating. Okay, so again y minus 0 we will write. Okay, so minus f u t square by, because integration of this will be t square by 2. Okay, assuming the lower limit is 0 every time. Okay, so we get some expression that the y displacement of the balls because of the x directional motion u, the y displacement is something like this. Okay, okay, fine. Now what is f? F is the Coriolis parameter, which is 2 omega sine phi. Here comes the dependence of the latitude. Omega we have derived. Okay, so 2 into 7.29 into 10 to the power minus 5 radians per second into sine of 43. Okay, this is what your F is. Okay, U. Okay, this U we need to actually we need to calculate this U velocity. Okay, so how will we do that? We'll see that. Okay. So your u, the zonal velocity, must be some x by time, right? This should be x by time. This velocity we need to calculate. Remember, to calculate. So fine, that is okay. Now, what should be? So what should be y? Should be the y, so that it those balls, the two balls just miss it. Okay, two balls just miss it. So what is happening? Here is the ball, another ball just misses it, right? So the if you take the center to center distance, okay, just misses means what? From one of the center of the ball, from considering one ball as the reference, it should be the radius, which is nothing but the 4 centimeter. So y for just missing y should be minimum. It should be 4 centimeter or 4 into 10 to the power minus 2 meters. Better to convert in the SI unit. Okay. So put this value in this equation and let's see what we get so far. Okay. So fine. Let us see. So y is 4 into 10 to the power minus 2, which is equal to 7 point, I'm sorry, 2 into 7.29 into 10 to the power minus 5 into u. So u, let us write, there is a t square and there is a 2. So this 2 cancel. Okay. Now 4 into 10 to the power minus 2 is equal to 7.29 into 10 to the power minus 5. Can we write this u as x by t? And this is t square. So this t and t will cancel. So we get 7.29 into 10 to the power minus 5 into x into t, which is 4 into 10 to the power minus 2. Perfect. Now, two unknowns. You have x and you have t. But I need one unknown, right? So what should I calculate? Look, they say that both these balls are thrown at equal velocities. So when they will just separate, it should be at the half of the 200 because this ball will also have same velocity, this ball also has same velocity. So at half distance, these balls must separate. So your h should be equal to the total distance 200 meters divided by 2, which is 100 meters. So there are many twists in this question. So it is 4 into 10 to the power minus 2, 7.29 into 10 to the power minus 5. This is 100 and this is some t. When you calculate everything, t will I think comes out about 8 seconds. Just check that you when you are calculating. Okay. And finally we need u, which is nothing but x by t. So x is 100 because for one ball by t is 8 seconds. So this will give you 12.5 meter per second. This is the answer. Okay. This is the answer. Okay. Now, question is what happens to this negative sign? There is a meaning of this negative sign as well. Okay. We have considered, so let's understand this. We have considered x as positive value, right? We have written plus 100. X is positive, we have considered. That means we are considering, so these two balls are there. We are considering this ball because this is the positive x. We are considering this ball. Okay. So this is, so if this is x, this should be the positive y and this is negative y. We know this. Okay. So when this ball is moving at some u, which is 12.5 meter per second, what is happening? In this ball, as the time elapses, there is a Coriolis force which is constantly acting in its perpendicular direction. Hence, it's, yeah, tell me. Question? Any question? Okay, fine. So, the Coriolis force is constantly acting to its perpendicular direction. And that's why the velocity, instead of moving straight, it tends to deviate from this direction and move like this. Okay. Now, if you have considered this ball, you have to take negative x, and you will see that this ball will try to tend to move towards this way. Now, since we have considered this ball, so it is moving in the negative y direction. That's why in this equation you have got a negative sign. So this negative sign also has a meaning. Okay. So what it represents is that at 43° north, when these two balls are approaching each other, and I'm considering this ball, it is moving southward, negative of y, which is true because that is the nature of the Coriolis force. Coriolis force, remember, this needs to be remembered. Coriolis force in northern hemisphere always acts rightward, and in southern hemisphere it acts leftward. Okay, this is very important. You can see it in through mathematics also, but this you must remember. So when you have in the earth, if you have velocity in the east-west direction like this, it the Coriolis force will make it deviate in this direction. Okay, just remember it. Or suppose you have a velocity in east to west direction, it will tend to move to its so this way. The winds will come this way. Okay, tends to move rightward. Okay, just remember this. Okay, I think I have not made it clear. Let me just. So suppose you have an arc like shape. Okay, and suppose this is so this is suppose north, this is suppose south, and this is east, this is west. Okay, let us consider like this. Now, if winds are blowing from north to south, right? North to south, northern hemisphere, where should be the Coriolis force? It should be to its right. So, wind will never come this, it will curve like this. So, winds will be in this direction. Similarly, from south to north in the southern hemisphere, if it was, it will be like this, to its left. Just remember this, it can be understood using mathematics also. Fine, this is a very important question. Just think about this question once more when the problem solving session gets over. Try to understand this question, and if you don't understand, then we can discuss in the next session. Okay, it's a pretty big question. Okay, let's come to so it's 12.5 meter per second should be the answer. Okay. The fifth one is also related to angular momentum conservation. Okay. So if an air parcel is carried poleward to 30 degrees latitude, starting from equator, conserving angular momentum as it moves, at what speed will it be moving when it reaches 30 degrees? Okay. So it starts from equator and it is moving poleward. Remember, every word is very important. Okay. So let's try to solve this question. So the fifth one, so it says that from equator to poleward, any air particle is moving, and this is suppose 30 degrees north. So in the positive y direction, so this is plus y. So in the positive y direction, it is tending to move. Okay. Now they're saying that what will be the velocity at 30 degrees north? Now, when you are talking about angular momentum conservation, so let's go to the question once again. Conserving the angular momentum as it moves, at what speed will it be moving when it reaches 30 degrees? Okay. So initially, initially at equator, we will assume that your zonal velocity means x direction velocity is zero. Actually, they want at 30 degrees north, what will be its u? And if suppose v is zero here and some v is here, okay, v is the y direction velocity. So at equator, air parcel is having some velocity through which it is moving northward, but after coming here, it is completely zonal. Okay, so I need u at 30 degrees north, and we will apply the conservation of angular momentum because that is what is asked. So conservation of angular momentum. So what is that? I will first write the expression and then uh, tell you that what is the actual thing. Okay. So angular momentum is due to two things. Generally for the Earth, angular momentum is due to two things. One is due to the rotation of the Earth and another due to the zonal velocity. Why? Because remember, angular momentum is what? R cross mv. Take again, I'm taking unit mass. You can take mass if you want. So it will be R cross some v, velocity. Now, in case of Earth, suppose this is your Earth, 2D Earth. Okay. So your some latitude, suppose phi, your zonal velocity or east-west velocity is cross. That is into the board. Okay. It is going into the board. Fine. Having some velocity u. Now look at this. This is your r, and there is a velocity perpendicular to the r into the board. So this is angular momentum is due to zonal velocity. Okay, this is due to the zonal velocity. And the second one is that the same Earth, because of Earth's rotation, so you have your omega here, right, with the angular velocity, and there is also an r, right? So this is the radius, and this is your r cos phi, suppose. Okay, so r cos phi into omega is the Earth's rotation. Okay, so this angular momentum is also due to Earth's rotation. So two velocities are there. One is the Earth's velocity, another is the parcel's velocity. Okay. So one is due to the Earth's velocity, another is due to the zonal velocity of the parcel, air parcel, or a volume of air. So angular momentum is always because of these two things. So when we write the expression, just look at the expression and you will understand. So let us consider radius of the Earth. Radius of Earth is, let's say, RE. So what we'll write is that RE cos phi, okay, into omega RE cos phi, right, plus u. So this zonal velocity is u. So this is from the parcel, air parcel, and this is due to the planetary rotation, right? See, this omega RE cos phi is coming from this, the second one, planetary rotation, because of the omega of the rotating speed of the Earth, and because of the this radius vector. So omega cross r is nothing but your angular momentum. Same way. Okay, but along with that, you have to multiply this. So this v is can be written as omega cross r. We all know this, right? So that is what we are doing. So this is the v, the omega cross r, planet. Okay, omega cross r. But angular momentum is r cross v. So this comes here. Okay, and this cross product goes because of the perpendicular direction. See, let me explain it better way. So r cross v, right? So can we write this as r v sine some angle between the sine angle. So the way we are defining, look at this u and this r vector, or if you make it like this, if this is your r, this will be what? R cos phi. We have seen this. See, this vector and u vector are perpendicular to each other. So this angle is 90 degrees. The sine 90 is 1. Okay. So that's why it will be Re cos phi into u. Second case, planetary rotation, omega cross r becomes omega r cos phi because these are perpendicular. Also, there is a r cos phi here. So that gives you this. Okay. So this is the angular momentum. Okay. Now we will conserve the conservation of angular momentum. We will take L1 is equal to L2. This is your conservation, right? Angular momentum conservation. So what we will do is that we take L1 as L at equator because that is the point from where parcel has started is equal to L2, which is at 30 degrees. These are constant, okay, according to the conservation of angular momentum. At equator, there is only a meridional velocity, right? Because the parcel is moving northward. So zonal velocity, so at equator, according to the question, u is 0. The zonal velocity is 0. That is x direction velocity is 0. V is having some meridional velocity is there. Y velocity is there. Okay, but u is 0. So we need u only. So L equator becomes what? It becomes Re cos of 0 into omega, right? Omega Re cos of 0 and your u is 0. So this is your L equator. Cos 0 is 1 omega Re. That's all. So this becomes omega Re square. Simple. Now at 30 degrees north, some u will be there which we will have to calculate. So L at 30 degrees becomes Re cos 30 degree omega Re cos 30 degree plus some u. So it will be Re cos 30 is root 3 by 2 into omega Re root 3 by 2 plus u. Equate this, that is L equator is equal to L 30 degrees now. So if you do that, you get omega Re square, sorry, square is equal to Re cos 30. Okay, let me not write again. So it will be root 3 by 2 into omega Re root 3 by 2 plus u. Now you cancel this. So you get omega Re and you can make this 2 by root 3 and this is omega Re root 3 by 2 plus u. So in that way, if you just calculating this way, so 2 by root 3 minus uh, yeah root 3 by 2 into omega Re is equal to Re is equal to u. So omega is, we have already calculated this, 7.29 into 10 to the power minus 5 radians per second. R is the radius of the earth. One must know this, 6370 kilometers. So into 10 cube meters. So just plug in the value and try to calculate. You will not get the exact expression, but I think it is 134 meter per second. You will get something similar to this. Okay, just try that. Uh, yeah, I have got 134 meter per second, but try your calculations. You may get this 120. So yeah, that is how the question has to be solved. This question is, yeah, sure. Tell me. Tell me. Hmm. Yes, this u is the air velocity. Air velocity. Yes, yes. Hmm. हाँ हाँ बिल्कुल बिल्कुल हाँ मास देखो मास यूनिट लेने का मतलब है कि हम लोग एक्सेलरेशन लेके बात कर रहे हैं बस मास यूनिट अगर लेना चाहते हो तो लो अगर नहीं लेना चाहते हो मत लो देखो एक एक एयर पार्सल जब हम लोग कंसिडर करते हैं ना, तो एक छोटा सा पॉइंट मास लेते हैं, इसका कोई शेप नहीं है, कुछ भी नहीं है। तो बेटर है कि इसको एक यूनिट मास लेके हम लोग कंसिडर करें, ताकि हमारा कैलकुलेशन इजी हो। क्योंकि देखो, जो हम जब हम लोग प्रेशर ग्रेडियंट फोर्स निकालते हैं या कुछ भी, हम लोग बोल तो रहे हैं फोर्स, लेकिन हम लोग कैलकुलेट करते हैं, देखो जो एक्सप्रेशन है दैट इज एक्सेलरेशन, हम लोग डेंसिटी से डिवाइड कर देते हैं। हाँ, तो एक्सेलरेशन हम लोग ज्यादा फोकस करते हैं। अब इधर आप मास अगर लेना चाहते हो तो लो, ले सकते हो। फिर भी अगेन यहाँ पे देखो कैंसिल हो जाएगा, एल इक्वेटर इज इक्वल टू 30 है ना, तो वहां पे फिर मास मास कैंसिल हो जाएगा। यही है बस, और कुछ नहीं है। इजी रखने के लिए अब मास का कोई वैल्यू दिया भी नहीं है। हाँ, तो इसलिए बेटर होगा कि हाँ, मूवमेंट के लिए। राइट। नहीं देखो, प्लैनेट का रोटेशन का पार्ट हमने ले लिया। ये जो ओमेगा आर कॉस वाला टर्म है, ओमेगा आर इंटू कॉस फाइव। हाँ, इसमें हम लोग प्लैनेट का जो रोटेशन है वो हमने ले लिया। लेकिन जो हवा है, हवा का एक एक पॉइंट मास अगर कंसीडर करो, एक 1 kg मास अगर कंसीडर करोगे एयर का, तो वो एयर का अगर कुछ वेलोसिटी है, वो हम लोग कंसीडर कर रहे हैं। क्योंकि वो भी वो आर के साथ परपेंडिकुलर में है, तो हम लोगों को लेना तो पड़ेगा वो भी। हाँ, तो वही है। तो ये हवा का जो एक पॉइंट, अगर मान ले हवा को, उस हवा का जो वेलोसिटी है दैट इज यू, उससे हम लोग एक एंगुलर मोमेंटम कंसीडर कर रहे हैं। और दूसरा है कि अर्थ का जो रोटेशन है उसके वजह से एक एंगुलर मोमेंटम कंसीडर, तो दोनों को मिला के टोटल एंगुलर मोमेंटम हुआ, जो कि हर लैटिट्यूड में कांस्टेंट होना चाहिए अकॉर्डिंग टू कंजर्वेशन। बिल्कुल, वही किया हमने। हाँ हाँ हाँ, क्यों क्यों लिखा है? हाँ, वो क्योंकि देखो, अगर तुम क्वेश्चन को देखोगे ठीक से, एन एयर पार्सल इज कैरिड पोलवर्ड। पोलवर्ड मतलब क्या है? नॉर्थवर्ड। नॉर्थवर्ड मतलब क्या है? मेरा दोनों कंपोनेंट ही नहीं है। हाँ, मेरिडियनल कंपोनेंट है, और मेरिडियनल कंपोनेंट में तो एंगुलर मोमेंटम लगेगा नहीं कुछ भी, क्योंकि आर के साथ वो परपेंडिकुलर उसमें है ही नहीं कुछ भी। आएगा तो जोनल वेलोसिटी के साथ ही आएगा और प्लैनेटरी रोटेशन के साथ ही आएगा, यही है। ठीक है, तो इसलिए यू को जीरो मैंने एज्यूम कर लो, जो कि कुछ भी है नहीं। हाँ हाँ, क्वेश्चन थोड़ा कंफ्यूजिंग है, बट यही मैं बता सकता हूँ कि क्योंकि पोल वर्ड लिखा हुआ है, तो जोनल कंपोनेंट को जीरो एज्यूम कर ही कर सकते हैं ना, कोई प्रॉब्लम तो नहीं है। हाँ, ओके। चलो, नेक्स्ट नेक्स्ट क्वेश्चन, लेट अस सी द नेक्स्ट क्वेश्चन। ओके, sixth one is, if A is 100 kilometer east of B, the sea level pressure at A is 100.1 kilopascals and B is 100 kilopascals, what is the pressure rated per unit mass? अगेन देखो, यहाँ पे पर यूनिट मास फिर से दिया हुआ है, तो इधर हम लोगों को कुछ कंसीडर करना ही नहीं, जस्ट सिंपल वी विल गो टुवर्ड्स द प्रेशर ग्रेडियंट एक्सेलरेशन। ओके, so let's see. This question is a bit easy question. So this is sixth question. Uh, so this is point B. Let us consider, and this is point A. Okay. At B has been asked that it is 100 kilopascals, and at A the pressure is 100.1 kilopascals. And if just let me see, A is 100 kilometers east of B. That is fine. Okay. So this is the positive x or eastward direction, and this is your westward direction. Then it is from B to the east of B at 100 kilometers. You have a point A whose pressure is this. Just zero point 0.1 kilopascals difference is there. Okay, and we know, so we are talking about zonal pressure gradient. So zonal pressure gradient. Okay, so zonal pressure gradient means it will be minus 1 by rho delta P delta X according to the pressure gradient acceleration or force per unit mass. Okay, so FPG pressure gradient. This is what we have to calculate, and rho is density of air. So density of air, which is nothing but 1.28 kg per meter cube. This we have to consider. Okay, and okay, so delta P delta X is easy to calculate. Make it like this: delta P delta X for easier calculation, for easier understanding. Okay, fine. So take any sign convention. Let us take the positive x value first. So 100.1 minus 100. Remember, this is in kilopascals, so into thousands pascal divided by 100 kilometers. So 10 cube again meters. So 10 cube 1000 cancel. You get zero point 0.1 divided by 100 pascals per meter. You get this 10 to the power minus 1 into 10 to the power minus 2. So get it this as 10 to the power minus 3 pascals per meter. And when you do 1 by rho delta P delta X, there is a negative sign, of course. So minus 1 upon 1.28 kg per meter cube. So just write it into 10 to the power minus 3 pascals per meter. Okay, so ultimately it will come out to be meter per second square, because pascals, if you just open up, it will give you that. And 1 by 1.28 will give you, I think, zero point 0.8 into 10 to the power minus, or it will be 8 into 10 to the power minus 4 meter per second square. And there is a minus sign. So why there is a minus sign? Very easy. So the answer should be magnitude is 8 into 10 to the power minus 4 meter per second square. But what is this negative sign represent? Negative sign is representing that your pressure gradient acceleration will be in the negative x direction. Why? Because this is at higher pressure. A is at a higher pressure, B is at a lower pressure. So where is the pressure gradient acceleration? It should be from higher pressure to lower pressure, right? The force should act from high pressure region to low pressure region, and this direction is negative x. That's why there is a negative sign. Okay, and magnitude is, I think the magnitude is required in this question. Yeah, something, I think 8.33 will come if you just do 1 upon 1.28. So 8.33 into 10 to the power minus 4, remember, meter per second square from A to B. That negative sign represents A to B. Okay, fine. Next is, which of the following is not an apparent force? Apparent force means pseudo force, which acts in only in the non-inertial frame or rotating frame. So, not a pseudo force. Coriolis force is a pseudo force. Centrifugal force is a pseudo force. Pressure gradient force is the only force which is not an apparent force. This Euler force or Euler force is also a pseudo force in a rotating frame domain, not related to atmosphere. You don't require that. Okay, just remember that when you have so many choices, don't get confused. Just when you know that one force is there, which is not a pseudo force, just write that pressure gradient force. That's all. It's a real force. We have seen that. Okay, this is a simple one liner. Yeah, the last question is the good question. What is the altitude at which artificial satellite orbiting in equatorial plane can be synchronous satellite? Okay, can remain above the same spot on the surface of the Earth. So this satellite is called the geosynchronous or geostationary satellite. That is, it will always above the same spot on the surface of the earth. That means I have given a hint in the I think the first problem solving session. So let's do this. So geosynchronous, geosynchronous satellite. Okay. So what is the geosynchronous satellite is that this satellite's orbital time period of rotation of the satellite is same as time period of Earth's rotation. Okay. So time period of Earth's rotation is known, that is 86400 seconds, that is 24 into 3600. 24 days, hours into 3600 seconds. So this is what you have. Same rotation period will be having for this geosynchronous satellite. And how will we calculate the distance or the height from the surface of the Earth, where the geostationary satellite or geosynchronous satellite has to be placed, is by or is through Kepler's third law. Okay, Kepler's third law of planetary rotation. So it's just saying that time period square is proportional to, actually it is the semi-major axis cube, but in case of Earth we will just take the r plus h kind of a thing. Okay, so in general t square is the proportionality constant is 4g 4 pi upon the gravitational constant g, mass of the Earth, into a cube. Okay, let us see what is the a cube. Okay, and so t will be equal to 2 pi. Uh, sorry. So it will be, I think there is some 4 pi square, something is there. You will see 2 pi root over a cube by gm. Something like this will come. Okay, so g is 6.67 into 10 to the power minus 11. This will be Newton. Uh, I think second square by kg square. Okay, let me, yeah, sorry, Newton meters, not seconds, meters. And mass of the Earth is, you can just search it in browser. It should be 5.97 into 10 to the power minus 24. Sorry, not minus, plus 24. Mass of the Earth. Okay, so GM is known. You need to, oh, okay, time period is also known, which is 86400 seconds. So based on that, when you calculate A, you will see that it is about 42,226 kilometers. A is 42,226 kilometers. But remember, we are talking about, this is Earth, this is the center of the Earth, this is the radius of the Earth, and your A is where the satellite has to be placed. Okay, this is the satellite. Okay, so let us say this is H, and what we have done so far is your, this is your A. So A is RE plus H. We need H. We need H. That is from the surface, how much is the distance of the satellite. So RE we know is 6370 kilometers. So H is A minus RE. So it gives you 36,000, approximately 36,000 kilometers. So from the surface of the Earth at a height of 36,000 kilometers, if a satellite is placed, its time period will be same as that of the, or if a satellite revolves or rotates around the Earth at the same rotation rate of that of the Earth, then your, the height at which it should be placed is 36,000 kilometers. Okay, so you have to use the Kepler's third law. this. Okay, fine. This will complete the assignment one, which has so many numericals. It took about an hour or so. Let's go to the second assignment and finish that one. Okay. So second, yeah. These are easy questions, and better I would refer to the second problem solving session. That will be easy for me. So I have actually derived all these things based on, I think, first, second, uh, particularly first and second. I have derived the entire thing in the second session. So if you have not looked into it, just look into the problem solving session link and try to see those derivations. Okay. So assignment two, first question says that in a rotating frame of reference, like the arc, the unit vector along east, that is I hat direction, is influenced by which kind of motion near the surface of the earth. So let me directly go, not here, let me go towards this one. In week two, I have derived this. Uh, yeah, so this d I hat dt. Okay, we have made so many things. We have tried to visualize the thing, and finally we have got that it depends on the u velocity, the zonal velocity. Okay, it depends on the zonal velocity. And I have, I think I have written also, depending on the sign of u, the I hat will be guided or changed. So if you now come to the assignment question, that influenced by which kind of motion near the surface of the earth. So it will be both eastward and westward. Why? Because the zonal velocity can be positive, can be negative. So positive means eastward motion, westward means negative. That's all. So I had the change in I had the unit vector along is influenced by the eastward and westward motion, both. Okay. Next is in a rotating frame of reference, unit vector along the north, that is the j hat. How it changes? Let us see again. We have seen this. J hat is a function of both x and y, and we have derived so many things. Finally, we have got it depends on both u as well as v, right? So, if you come to the question, see the only option which I can see is that both northward and eastward. Whether it is if it is said that both southward and westward, that is also true. Okay, so careful. So both northward and eastward motion is the right answer. That is u and v guided. All other options has either V guided or U guided. So the C option is the only correct option. Okay. So I'm not going into the details because I have already shown this. Third is a question. This is a very easy question. Suppose the wind is blowing southward in the northern hemisphere. Okay, in the northern hemisphere, the wind is blowing southward with a velocity of 20 meters per second at a distance of 100 kilometers from the lowest pressure point. So, magnitude of centrifugal force, C again per unit mass. So, what should I do in that? Let's come to week 3 where I have this one. Okay, so this is week 2 assignment. Okay, week 2 assignment, question number 3. Okay, so couple of things which are being asked, that is to calculate centrifugal force. But it's better to understand what the question is saying. Why centrifugal force? So there are winds we know that is in circular motions, right? For example, in the case of cyclone, there is a circular motion. But interestingly, they're saying that there is a point from the lowest pressure point, it is at 100 kilometers, okay? And the velocity, so the velocity is here. That is, this is the northern hemisphere. Okay, this is the northern hemisphere, but the velocity is southward. So this is y, negative y, that is south, and this is north. Okay, we are above the equator, so northern hemisphere. So wind is like this, and this is the lowest pressure point, this center. and the radius is 100 kilometers. So you know when there is a circular motion, there must be some centrifugal force. That is what we need to calculate. So centrifugal force Fc per unit mass, or let us write per with mass. That is mv square by r. Right? So per unit mass will be the acceleration, which is v square by r. You have been given the velocity. So v is 20 meter per second. So 20 into 20 divided by r. R is 100 kg. Okay. So you get 400. Remember, this is meter square per second square divided by 100 kilometer. So it has to be this converted into meter. So all these things goes. It will be 4 into 10 to the power minus 3 meter per second square. That's all. This should be the answer. Okay. So yeah. Okay. Fine. So this is 4 into 10 to the power minus meter per second square. Okay. Fourth question. Which of the following forces can cause horizontal gradient wind? I don't know whether in the NPTEL, this advanced atmospheric physics, this gradient wind, geostrophic wind has been shown or not, but the couple of questions are there which considers this. Okay, so horizontal gradient wind. Remember, this is I think the fourth one. See, gradient wind is the balance of three forces: pressure gradient. One is the pressure gradient force, number one. Number two, Coriolis force. And number three, centrifugal force. Because there is a rotation here. Okay. So gradient wind is something like this. Suppose you have curved isobars. Okay. Isobars means constant pressure lines. Right? If you have curved isobars and your velocity is parallel to these curved isobars, this kind of a wind is called the gradient wind. Okay, which because of this curvature, there will be a centrifugal force. Otherwise, Coriolis and pressure gradient will act. But for geostrophy, the balance is between two forces. Pressure gradient, one is the pressure gradient force, and the second is the Coriolis force. Okay, and this will happen only when you have straight isobars, P1, P2. We have straight isobars. Okay, this is one of the characteristics of the geostrophic wind. So this has straight isobars, no curvature. Okay, because when curvature comes, centrifugal will act. Otherwise, this is only the balance of, it will blow parallel to the P1 and P2 with a balance of the pressure gradient force and centrifugal, sorry, Coriolis force. That's all. Okay, so let us say that P1 is less than P2, so the pressure gradient will be here and centrifugal, sorry, Coriolis will be Coriolis, and this is the pressure gradient. That's all. Okay, so this is what you call as the geostrophe. Okay, so if you now go into the question, whichever can cause the horizontal gradient wave. So you have pressure gradient, centrifugal, and Coriolis, both. Fifth question is work done by Coriolis force on atmospheric system. Remember, for any pseudo forces, whether it is centrifugal, Coriolis, or any other pseudo forces, work done by pseudo forces is always zero. Work is done only by the real forces, so it is always zero. So any other force, if it is given and there is an option of work done, it is always zero. So just one line. Sixth, in a controlled volume, the total thermodynamic energy is considered as, uh, I think it is there in the second week lecture, it is the sum of the internal energy as well as the kinetic energy. Today we will see, we had some 30 minutes, 35 minutes, we will see that. Seventh is geostrophic wind is observed where isobars are straight, this is right. Where isobars are curved, no. Geostrophy is not seen when isobars are curved. But where Coriolis force is non-zero, yes, this is a factor. So A and C are the correct option. So D. Okay. Eighth is the external body force which can act and control volume. So external body force is only Coriolis and gravity. Viscous force is the surface force again. So B and C are the correct option. So these are all simple one-liner thing based on previous knowledge. So what we have done so far is that we have seen the assignment questions, we have just discussed the one-liners, and we have solved the numerical problems. Okay. Now, we will come to this total thermodynamic energy. We will try to see that what is your this thermodynamic energy equation and all these things. Okay. And briefly talk about the scale analysis. I might not, because of the time constraint, we might not talk about much about the scale analysis. You have to see the derivations of that. But I'll give you a simple hint of scale analysis. Okay, so let's start with your thermodynamic energy equation. Give me a minute. Okay. So uh, let's try differently. Okay, let's see the thermodynamic energy equation. See, there are many ways to understand this energy equation. So, what we will see is that we will try to use the first law of thermodynamics. Okay, first law of thermodynamics, which talks about the energy conservation in a particular system. So, what is that? Cp dt minus alpha dp is equal to dq. Okay, what is alpha? Alpha is 1 by rho, which is nothing but volume per unit mass. Density is mass per unit volume, alpha is volume per unit mass. See, first law of thermodynamics, we can write this also, Cp dt plus Pd alpha is equal to dq. You can write this. If you apply ideal gas law, ideal gas equation, you can convert it into this. Okay, and let us start from here. So dq is equal to Cp dt minus alpha d. Okay, alpha is called, this is called the specific volume. Specific because per unit mass. Okay, so this is just naming. Okay, so what we will do is that, so Cp minus Cv is equal to R. So, or you don't need this. So, what we will do is that we will differentiate with respect to time. So dq dt is equal to Cp dt over dt minus alpha dp by dt. Perfect. This is okay. Now dq dt, the heat change rate, we generally call this as the diabatic heating rate. J is equal to Cp dt over dt minus alpha. What I do here is that we make it dp dz into dz dt. Okay, so you get dp dt by dt minus alpha. Dp dz is, according to hydrostatic approximation, it is minus rho times g, and dz dt is W, the vertical velocity. Okay, so hydrostatic hydrostatic approximation is that dp dz is equal to minus rho g. Okay, so if you do this, you get Cp dt by dt minus minus gives you plus alpha into rho is 1, so it will be g times w. Now what we do is that we divide by Cp both sides, so you get dt by dt plus g by Cp into w. In thermodynamics, this g by Cp is called the dry adiabatic lapse rate. Dry adiabatic lapse rate. Lapse rate is the change in temperature with height. How the dry adiabatic parcel, air parcel, is changing temperature with height is your gamma d, and it is a fixed quantity, so that's why it is g by Cp. Okay, so J by Cp is equal to dt by dt plus gamma d into W. Now, total derivative can be written as the local derivative plus advection term, so delta T by delta T plus V dot grad T plus W delta T by delta P, oh sorry, delta Z plus gamma D W. Alright, this is okay. Now, what we do that, we will combine both, so it will be delta T by delta. Okay, this V vector is nothing but U comma V. Only the horizontal velocity. The vertical velocity we have already taken care of. Dot correct T. Okay, so here we can write delta T delta Z plus gamma D. Okay, now gamma is the actual lapse rate, and that can be written as minus delta T by delta Z. How the temperature of any parcel which is not adiabatic or dry adiabatic or something is changing with. So this is what you get. So delta T plus V dot grad T plus W times gamma D, you write, and delta D delta Z can be written as minus gamma from this. So this becomes J by 6. This becomes your thermodynamic energy equation, and this gamma D minus gamma is the static stability of the atmosphere. Why it is called static stability? Because of this gamma D and gamma, this difference will guide whether the air parcel will move due to its buoyancy or it will settle down. Okay, so this is perfectly thermodynamical quantity. Okay, so this is therefore called the thermodynamic energy equation. Thermodynamic energy equation. This is one of the things. Okay. Now, there are many modifications of this thermodynamic energy equation, and there is another way of deriving the energy equation. So, we will see that. But let us also see how we can write the thermodynamic energy in terms of potential temperature, because it is there. Okay. Potential temperature. I will just write the mathematics. Okay. So it is denoted as theta is temperature into P naught. Essentially, this P naught is taken as 1000 hectopascals to P, and this is R by Cp. This R is nothing but 287. Okay, joules per Kelvin per kg, and Cp for dry air these are taken. So this is 1005 joules per Kelvin per kg. This theta is the potential temperature, which I have already. This is the dry air temperature. Okay. P naught is generally 1000 millibar or 1000 hectopascals. Okay. So based on this, we can again write the thermodynamic energy equation can also be written like this. Let's see. So what we have started with CP. So another way, one of the ways is this, where you can see the temperature involvement. Another way is that Cp dt by dt minus alpha dp by dt is equal to dq dt, which is nothing but j. We have already seen that. Now what we are doing is that we divided with temperature. So Cp by T dt by dt minus alpha by T dp dt is equal to J by T. Okay. Now, ideal gas equation says that pressure into specific volume is equal to R into T. Okay. So, based on that, can we replace alpha with this RT by T and put it here? So, Cp by T dt by dt. These are mere derivations, nothing else. Just look into this. It doesn't matter. Just RT by T dp by dt is equal to J by T. Okay. And finally, can we write this as this Cp ddt of log T? Because if you differentiate log T, it will be 1 by T dt by dt. So we can write. And okay, there is a T here. So this T and T cancel are ddt of log P, which is equal to J by T. Fine. Now, use the definition of potential temperature. Theta is equal to T, P naught, which is a constant, P, which is varying, R by C. So now what we will do is that take log of in both sides. So log T plus R by Cp log of P naught minus R by Cp log of P. Okay, differentiate with respect to time. So d dt of log theta ddt of log T ddt of this is a constant quantity, so it will be 0 minus this is not a constant, so R by Cp ddt of log P. Perfect. So what we do is that we multiply Cp, so ddt of log theta is equal to Cp ddt of log capital T temperature minus R ddt of log P. Now take a look at the right hand side. See, this is this J by T. So what we get finally is that Cp ddt of log theta is nothing but heating rate divided by temperature. J by T. Okay. And finally Cp by theta d theta dt is equal to J by T. Fine. So this is what you get, the final expression. And finally, you can also write this d theta dt as delta t plus u delta theta delta x plus v delta theta delta y. That is local change plus advective change. Delta theta delta. Okay. And finally, go through with the expressions. So why am I doing this? Is that in the week 3 lecture, at the very end, I think the scale analysis is being performed on this equation. So it's just a simple derivation to understand that how this is being derived, and then scale analysis will be performed. So that you can easily understand. Okay, mass conservation we have already seen in the last session. I will derive one more thing about the just energy conservation equation. Okay, so we have looked at thermodynamic energy equation in both ways. Generally, this will be applied in the week 3. Okay, and finally, we go towards the uh, energy conservation. Okay, energy conservation equation. And then after deriving this, I will just give a hint of the scale analysis and then we'll list down something and just give you a simple hint of what the scale analysis means. Then you can go through the week 3 lectures and try to solve the assignment. Okay, so let's say that E is the internal energy per unit mass. So what is this internal energy? Is the kinetic energy of the micromolecules present in the system. When these molecules get stronger or the kinetic energy is more, the internal energy becomes more, the heat becomes more. Okay. So this is what your internal energy. So internal energy can be therefore written as the density times E, the internal energy per unit mass, times dV, the volume. Similarly, there is a potential energy in the atmosphere that will be rho phi dV, which is due to the gravity Gz. Phi is Gz. Okay, and there is a kinetic energy of the macromolecules that is half. That is the air particle or something. Okay, so this will be half rho u square dV. Remember, this u is all, so it's a vector with a magnitude square. Okay, so this u is the vector. So it is u, v, w, everything. Okay, so now the total energy that is rho dV u square by 2 plus phi plus e will be equal to the work done. We know that net total energy is nothing but equal to the work done. This is known. So this is the energy conservation equation. Okay. How to derive this is that to start with the momentum equation. The best way to start is the momentum equation. Why you will get to know. So du dt, as I have told you, that u is nothing but UVW, everything included, is equal to the pressure gradient, acceleration, minus grad phi, which includes g, the gravity, centrifugal force, everything, and minus 2 omega cross u, the Coriolis force. Other forces are not there. Friction is neglected. Also, although friction also produces some energy, but it is neglected here for simplicity. What I do is that dot with u. So u dot du dt. So what it will be? Minus u dot grad p by rho minus u dot grad phi minus u dot 2 omega cross u. Now just see this. This is omega. This is u. Okay. So omega cross u will be something perpendicular to the board or towards the board. Okay. That is the direction. Now, if you dot with u, so u is perpendicular to this cross direction, so therefore this will be, dot product will be 0 because there is a 90-degree between the angle is 90 degrees. So dot product when the angle between the two vectors is 90 degrees is 0 because cos 90 is 0. So this is gone. What about this? Can I write this as d dt of mod u square by 2? Right? We can do this is equal to this rho, which is here, can I multiply on both sides? So rho minus u dot grad p minus rho u dot grad phi. Okay. Now, thing is that d phi dt is delta phi delta t. Okay. Plus u dot grad phi. Right. Total derivative, local derivative plus u dot grad phi. But for potential like phi, if it is grad phi is equal to g, right? The gravity, its potential is does not vary with time. Local change is 0. Okay, so that's why this is d phi dt is nothing but u dot grad phi. Whether it is, if you just remember, whether it is electrical forces, or what you call as your this potential potential energy kind of G. These are uh, a kind of a conserved quantity. So it can be written as gradient of some potential. When you can write it as gradient of some potential, its time derivative generally is zero. Okay, it's a potential. It has nothing to do with time. Fine. So this is what you have. Okay. So rho d dt of mod u square by 2, okay, plus rho u dot grad phi can be written as d phi dt. Just write it. That is equal to minus u dot grad phi. What is this? Kinetic energy, right? Or kinetic energy per unit mass. So just write it, mod u square by 2 is kinetic energy per unit mass, because half mu square is kinetic energy, plus, can I write this as phi? The potential energy is also included, minus u dot grad. Let's see the right hand side. That is u dot grad p. Can we write del dot u times p as u dot grad p plus p del dot u? We can write this. It is just a simple equation. So u dot grad p is equal to del dot up, just rearranging things, okay, minus p del dot u. Okay, this we can write from this equation to this. Now, according to the conservation of mass says that minus del dot u is 1 by rho d rho dt, correct? Use first law of thermodynamics. There are so many connections. Okay, first law of thermodynamics says that dq is equal to cv dt plus pt alpha. Alpha is specific volume. I have already explained. You can write pdv also. That's okay. So 0, or I'm writing it dv. 0 for adiabatic process cvdt plus pdv. So this is adiabatic. One of the assumptions. So minus pdv is equal to cvdt. Okay. Keep it closed. We will use it. So p dv dt, if I just differentiate, will be equal to cv dv sorry, dt by dt. Great. Let's keep it like that. Now, let's talk about 1 by rho d rho dt. Can I write rho is equal to 1 by v? Because this v is volume per unit mass. So this will be v, this will be dt of 1 by v. When you differentiate, you get minus v by v square dv by dt, which comes out to be minus 1 by rho, because v cancels, dv by dt. Okay, this is what you get. Fine. Now, minus p del dot u is equal to p by rho d rho dt, which is equal to minus rho p dv dt. How we are writing this? See, this is nothing but minus rho dv dt. So that's all. There is a p which I am taking here. 1 by root e rho dt is minus rho dv dt. That's all. That is what we are writing. So we are combining this with this. Okay. So we are getting something like this. Now, minus p dv dt. Look at this with a minus sign is cv dt. So it will be rho times cv dt by dt. What is that? Minus p delta t. So finally we have got this expression. Therefore, u dot grad p is del dot up plus rho cv dt by dt. Perfect. Now, why plus? Because there is a minus p del dot u, so we are just writing it. Okay. Let's come back to this equation. Okay. So let's write this. So rho d dt of u square by 2 plus phi is equal to minus u dot grad p. Right? This was the expression. U dot grad p we have found out. So is rho cv dt by dt minus del dot u into p. So just take it on the right hand side. Dt u square by 2 plus phi plus cvt is nothing but minus del dot u. So what we can say here is that this is kinetic energy, this is potential energy, and this is the internal energy, CVT. So the total energy ddt of E into rho is not conserved. It depends on this. But globally, when you do integration of this divergent term will go because there will be a complete global integration. So this term will go. There we say that energy conservation exists. So in the global scale, it exists, but materially it is not conserved. So energy conservation or energy, total energy, is not materially conserved. Okay. But global integration, globally in R, total energy is conserved. Because the divergence of UP is there. So if you think of a control volume and integrate all over the control volume, the amount which is coming, the same amount which is going, it cannot be violated. So there this term will go to zero and the total energy becomes constant. Okay, so this is something different. Let's talk about the scale analysis and stop the lecture today. Okay, so I have one slide. Let me see where. Yeah. So this is the different atmospheric scales. So you can see that there are small turbulent eddies which has a time scale. So this is the time and this is the spatial scale. So this this micro scale is about 2 meters, some few meters. Okay, and it acts in the time span seconds to minutes. Very small eddies. You will see that day to day life. Sometimes what happens is that some leaves are moving in circular motion in a very local scale. That those are small turbulent eddies. Next is minutes to hours. When you see large cumulonimbus clouds, tall clouds are formed and thunder showers happening. These happen generally in some hours, minutes to hours. And what is its time scale? Over a region of 30 kilometers, 10 to 30 kilometers, right? So this is called the thunder shower. And these are generally the mesoscale. Okay. Next comes is the synoptic scale, where tropical cyclones can be seen. Okay. Monsoon depression, tropical cyclones. These are generally for a week. Okay. Some few days or weeks. And synoptic scale is about 1,000, more than 1,000 kilometers. It's written 10 to 20,000, but it's more than 1,000 kilometers. And another is the long waves, planetary scale, about 5,000 kilometers. So it is actually global, circumferring the globe. So long waves mean some jet streams are there. Okay, these are global. So it's more than a week. Okay, so it's global. In fact, you will see year round there is a jet which blows in the subtropics. Okay, so those are the long waves. So these are different scales of motion. Okay, now whatever scale analysis we do is to reduce the terms in the equation. For example, we have seen momentum equation. There are lots and lots of terms, right? Even if you don't convert it into spherical polar coordinate, Cartesian coordinate, there are many terms: advection terms, local terms, pressure gradient force, Coriolis force, right? Gravity. So there are so many terms. Can we reduce it based on some scale analysis, some average value? If we have some observation of those variables and have some average value for a particular scale, can we reduce this momentum equation? Can we reduce continuity equation? So those are the things which we do in the scale analysis. So we will generally see for the synoptic scale that is of this order and for mid-latitude region. Mid-latitude means typically from 40 degrees or 35 degrees to 65 degrees in that zone. Okay, so let's go here and try to write the scale analysis. Okay, the scale analysis is generally performed to reduce the terms in any equation, physical equations. So we have seen so many equations like momentum equations, mass conservation equation, energy conservation, thermodynamic energy equations. So in those equations, can we reduce certain terms which are not very important? That is what our main aim is. Okay. Okay. Next, the scale analysis. I will write some values. Values are for mid latitude, mid mid latitude, which is around 35 to 60 degrees in both hemispheres. Synoptic systems. Okay. Synoptic systems means more than 1,000 kilometers. And time span or time scale is roughly about a week. Okay. So let us jot down some values. So one is that your velocity. Velocity means horizontal velocity. Remember, this is horizontal velocity. Horizontal velocity. This can be this U. I am writing U, but it can be U as well as B. Zonal and meridional. So just write zonal or meridional, but not vertical. Be careful. So U value is typically 10 meter per second. Okay. Now vertical velocity W is generally 10 to the power minus 2 meter per second. Okay. Next, length scale, that is x distance or something. So any phenomena which is happening in the synoptic scale in the mid latitude, what is the general length scale? Is 10 to the power 6 meter. Okay. Both zonally and meridionally. Okay, just horizon. Remember, this horizontal means both zonal as well as meridional, means x and y, both, but not z. Be careful. Height, that is the z scale, is about 10 to the power 4 meters. Okay. G, we all know, gravity, 10 meter per second square. Okay. F, the Coriolis parameter, 2 omega sine phi. This phi we generally take as 45 degrees because mid latitude. So this is about 10 to the power minus 4 per second. Okay. And change in pressure in horizontal direction x or y is about 10 hectopascal, and delta P in z is about 1000 hectopascal. Okay, just remember these two. What else? T. T can be found out L by U if you do that is t, distance by velocity. So what it will be? 10 to the power 6 by 10, which is 10 to the power 5 seconds. General time. So you can understand this, right? Few days. So this is 10 to the power 5 seconds. Next is nu. It is the coefficient of friction. So or viscosity, coefficient of viscosity, meter square per second. Okay. And another thing is that change in density to its mean is about 10 to the power minus 2. It should be kg. No unit. Kg per meter by kg per. So these are typical values that you can see. Or another thing is there, delta P divided by rho. That is about 10Q. You can derive this. This is not a big deal. Okay. So these are typical values. Okay. Now, if you want to apply it, let's take a momentum equation, horizontal momentum. So X momentum equation, let's say. I'm just applying in one. You can see many in the upcoming lectures. We will do one by one. So let's take it, say, Cartesian coordinate, delta U delta T plus U delta U delta X plus V delta U delta Y plus W delta U delta Z is equal to pressure gradient, the zonal direction. Okay. Then let's leave Coriolis force for the time being. It is not required, or you can. We can take the horizontal Coriolis force. This will be FB plus FB. And anything else? Friction we are neglecting for the time being. That's all. Okay. So this can be written as, so delta U. U is, U scale is U, capital U. T is time plus. Second term, U, delta U delta X is U by L. Like this we will write. Third term, V. V is the meridional velocity. So same U we will write, and delta U delta Y, U by L. Because Y and X lengths are same, Y and X velocities are same. Next, W is W, U by Z, so H, height. Okay, this is minus delta P by rho L plus F we know and U. That's all. So just put each and every value and try to see which term is dominant. So 10 divided by 10 to the power 5. Second term, 10 into 10 by 10 to the power 6. Again, 10 into 10 by 10 to the power 6. Then W is 10 to the power minus 2 into 10 by 10 to the power 4 is equal. Minus delta V by rho is 10 to the power 3 divided by 10 to the power 6. And finally, you have the FU, that is 10 to the power minus 4 into 10. So what you get? 10 to the power minus 4, right? This is 10 square. So this is also 10 to the power minus 4. This 10 to the power minus 4. What about this? 10 to the power minus 5. Okay. This 10 to the power minus 3. And what about this? 10 to the power minus. So we see that right hand side these two terms is dominant. All other terms are one order or two order magnitude smaller than this. So we can reduce the above equation to only this minus 1 by rho delta p delta x plus f equals 0. And if you just remember, this is nothing but geostrophic balance. This is the power of scale analysis. It reduces the horizontal momentum equation to only a small geostrophic balance. Okay, so there are many other things we can see in the next sessions. Okay, so I'm stopping here. Any question is there? You can, or We can meet in the next session after you look into all these things. Okay. So let me just stop the recording.